Okay, this is the last section, um, total internal reflection, which is 34.7. Um, let's need to make sure I have my notes, but let's share the PowerPoint. And I lost it. Oh, I'm gonna. I'll probably show you some quiz. Uh, Here we are. Sorry about that. Total internal reflection. Now, this is from a light in going from a slow index of refraction to a fast um, index of refraction. We get this phenomena. As the angle of incidence theta 1 increases, the angle of refraction theta 2 increases until theta 2 is 90 degrees. Ray 4 is this one right here. The dashed line indicates that no energy actually propagates in this direction. You can see as this angle bends, there's a point here that at 4 that it stays internal, and these other angles, like 5, it's all internal. So the angle of incidence producing an angle of refraction equal to 90 degrees is the critical angle, theta c. For angles greater than theta c, all the energy of the incident light is reflected. It all stays within the medium. So N1 sine theta critical is equal to N2 sine 90 degrees equals N2. So sine of theta critical is equal to N2 divided by N1 for N1 greater than N2. Okay. The total internal reflection and the diamond. The critical angle for the total reflection, total internal reflection is small when N1 is much, much greater than N2. Example, the critical angle for a diamond in air is equal to 24 degrees. Any ray inside the diamond that approaches the surface at an angle greater than 24 degrees is completely reflected back into the crystal. This property combined with the proper faceting causes diamonds to sparkle. Angles of the facet are cut so that the light is caught inside the crystal through multiple internal reflections. Multiple reflections give light a long path through the medium, giving substantial dispersion of the colors inside. By the time the light exits through the top surface of the crystal, the rays associated with different colors widely separated from one another. Now, the internal reflection of cubic zirconium, zirconia has a higher index of refraction than the diamond, but it can be made to sparkle like a diamond. If you put the jewel, if you're not sure if it's a diamond, if you put it in corn syrup, you can the difference in N for cubic zirconia and that for corn syrup is small, so the critical angle is great. More rays escape sooner, and the sparkle it just completely disappears when you put it in corn syrup. Real diamond does not lose its sparkle when placed in corn syrup. So if you're a little worried that you got a cubic zirconia instead of the real diamond, put it in corn syrup. All right, now here's a test. In the figure, 5 light rays enter a glass prism from the left. How many of these rays undergo total internal reflection at the slanted surface of the prism? Well, you can see that 3 of them have escaped. There's 5 rays, 3 of them have escaped at the right-hand surface, but 2 of them have not escaped. They all come out the bottom, but 2 of them don't come out the right side. So it's 2. The answer is 2. 2 of these rays undergo total internal reflection. Now, suppose the prism in the figure can be rotated in the plane of the paper. For all 5 rays to experience total internal reflection from the slanted surface, the prism should be rotated clockwise or counterclockwise? Well, it might be counterintuitive, but it's counterclockwise. As you turn that, the angle will be greater, and the counterclockwise rotation of the prism will cause the rays to strike the slanted side of the prism at larger angle. When the 5 rays strike at an angle larger than the critical angle, they all undergo internal reflection. Okay, optical fibers. Optical fibers use the principle of total internal reflection. So you see that you have the light bouncing off the sides of the fiber optic. You have the glass or plastic core, you have the cladding, and you have a jacket. I used to have, if I find my fiber optic, I'll bring it to class and demonstrate it to you, how you can see the fine, you can see the light, even though it just looks like a cable. So optical fibers are used in communication. Uh, the so it's a, you can put information on the optical fibers. Um, the Oops, let's see what I. So the on the left hand is a bundle of optical fibers gathered into uh, an optical cable that can be used to carry communication signals. And many computers and other electronic equipment now have optical ports as well as electrical ports for transferring information. We used to use the optical fibers for insulation. We'd have a high voltage side, and we wanted to isolate from the high voltage side, so we would communicate through optical fibers. And I think, yeah, that's the end of the slideshow. That's the end of the lecture.